This presentation from Dr. Gerard Borello, Inter AC, introduces D3S software to help in designing and simulating DART acoustic environmental test. DART test system quick description. DART is an acronym for Direct Acoustic Radiation Transfer. It refers to a specific type of acoustic qualification test of payloads, named DFAN, DFAX or DFAT in the available technical literature, the latter being the most popular, but now registered as a trademark. DART is an alternate solution to reverberant chamber test for acoustic qualification of spacecraft to random noise generated at launcher liftoff. DART hardware is made of a swarm of high-powered loudspeakers located at a distance from the payload test specimen as sketched in here below picture. Next slide. Now a quick review of benefits and risks of DART tests. Main benefits are lowering qualification cost, because tests can now be performed on payload integration site and thus avoiding transportation to an external test center equipped with reverberant chamber. There is more accurate control of qualification sound pressure levels or SPLs at set of predefined microphone locations. Several risks may be quoted as follows. SPLs outside controlled points are specific to DART setup. There is some phase interference due to radiation of correlated speakers. The impinging incidence distribution of acoustic wave differs from classical reverberant chamber, to which payload structural response is sensitive, as shown in the next slide. Consequently, a DART test is losing the quality of universality provided by a reverberant chamber test, when analyzing acceleration responses. It induces extra variance in acoustic qualification, that is an expected vibrational difference between a given DART configuration and reference levels provided by reverberant chamber tests. Introducing DART test in the qualification process is requiring update of past numerical and experimental expertise in deriving actual liftoff qualification levels of spacecraft. Next slide. The sensitivity of sandwich wall to incidence is illustrated by the expected RMS response of a standard sandwich panel under different acoustic wave patterns. RMS acceleration is predicted here with C+ software under acoustic plane wave incidence, 0 degrees, 40 degrees, 80 degrees, and diffuse, in 1/3 octave bands, for a payload sandwich, aluminum skin 1 mm, honeycomb core 20 mm. Potential variations of RMS acceleration lies in between 2 to 10 dB from diffuse field prediction. Next slide. D3S software is useful for DART risk analysis. It will provide to the user enlightening information such as numerical simulation of DART sound field at any location, direct solve from input spectral voltages to local SPLs, inverse solve from specified SPLs to required input spectral voltages to be applied to the various loudspeakers. Regarding pressure level scattering in the DART field, differnet analysis may be performed through prediction of interferential acoustic field, include reflections from the ground, numerical analysis of propagating waves by the DART swarm, 2 DFAT of SPL distribution on reference movable panel surface. Export as incident wave distribution to analyze vibrational response to DART sound field. Next slide. Design and simulation of DART systems. D3S has two major capabilities, design and simulation. First, design for building its own DART system. Second, simulation as D3S models the electromagnetic behavior of swarm of speakers from input voltage to delivered acoustic pressure. Loudspeakers are described in D3S by their TLS parameters, easy to retrieve from simple electromagnetic impedance measurement. Any suitable speaker on marketplace can be used in D3S to build a model of the DART setup. Next slide. D3S software user interface. D3S is a Windows app, with 3D GUI and relational database for describing object properties. Properties are accessed through a tree browser. Various model configurations may be created from the browser. Next slide. Design and simulation of DART systems, the D3S model. Simulation for analyzing field response. Quick D3S setup modeling by arranging speaker drivers in cabinet cluster. Prediction of all system parameters such as electric consumption required for reaching given SPL, voltage and current spectra of all speakers, velocity spectra of speaker diaphragm levels at controlled points for a set of discrete controllers, independent random signals driving the subset of cabinets. Radiated power from both D3S cabinet swarm and from individual cabinets. Dense mapping of SPL on a movable rectangle associated to 2 DFAT. Impulse audio responses in time domain. Next slide. Building models in the 3D GUI of D3S. Defining electromagnetic drivers. Input of their TLS parameters. Adding compression chamber and horn to some drivers. Creating cabinets containing required drivers. Associating cabinets to control voltage signals. Automated generation of DART-type configuration from parametric geometry. Next slide. Analyzing D3S spectral outputs. RMS electric voltage on output are filtered by crossover filters associated to drivers. RMS SPLs at controlled nodes may be graphed as well as electric powers and radiated acoustic powers related to the system configuration and all individual drivers. SPLs are automatically output with settable meshing on parameterable spacecraft reference panel. Next slide. Analyzing D3S spectral and 2D FFT outputs through motion of driver diaphragms. RMS and 1/3 octave spectra of displacement, velocity, acceleration of driver diaphragms. On the reference payload panel, walled pressure SPLs are mapped, which provides the mapping of SPL distribution by analyzed frequency. The mapping of Fourier's transform coefficients of the SPL distribution in the wave number domain. Latter mapping is related to the local distribution of impinging incidences on the reference payload panel. Next slide. D3S calculation flow has been submitted to verification test in surrounding anechoic and test environment. Through test campaigns with Airbus Defence and Space using set of JBL cabinets. These tests were performed on 2 sets of cabinets, subwoofer and 3-ways cabinets. To start with, the TLS parameters of the various drivers, subwoofer, woofer, medium, and tweeter, were identified experimentally using standardized impedance method from audio industry. Then the cabinet models were built up for simulating the radiation of subwoofer and 3-ways cabinets. Quality of the simulation was established by cross-comparing measured and predicted SPL pressures at distances along with directivity factor of radiation and diaphragm velocity. Several test configurations were involved using single cabinet radiation, 2 interacting cabinets, 1 passive, 1 active. Pictures are showing the model with passive-active cabinets and comparison results between test and simulation. The velocity is measured on the passive driver diaphragm at various distances of the active one and compared to test. Due to the use of low voltage levels, the comparison is only valid within the driver bandwidth. Predicted passive diaphragm velocity is blue curve and related predicted SPL in the near field of the passive diaphragm is at 2 meter distance from active cabinet, predicted SPL is red curve. Next slide. D3S is also implemented with active noise control capabilities, ANC. In the here below example, a given SPL is simulated at a set of distant points from a source cabinet. Voltage state at set of extra cabinets, the anti-sound drivers, is identified by ANC solver. The inverse ANC voltage outputs are then re-injected in the anti-sound drivers and effectively cancel the given SPL by an outphase SPL, as seen in the phase graph. Pictures are showing model for generating the source SPL to be cancelled out. The found RMS modules of source and anti-source signals. The model of ANC cabinets to cancel out SPL from source. The phase of source and anti-source signals. Next slide. Synthesis. D3S for Dart design and simulation is an inter-AC software validated in collaboration with Airbus Defence and Space. It has been designed for Dart system modeling. Starting from elementary electromagnetic driver parameters, called the TLS parameters, including drivers in user-defined cabinets, and creating cluster of cabinets from user-defined geometrical configuration. It is helpful for the design of Dart by solving both direct and inverse problems. Starting from voltage, it provides SPLs, diaphragm responses, and electric currents. Starting from specified SPLs, it provides diaphragm responses, electric currents, and voltages. Given a number of independent specified voltage signals between controllers, each of them associated to a subset of cabinets, it provides the random or deterministic response of the system. From previous solutions, wave interference effects are predicted within the generated wave field. The latter correlated pressure wave field can be exported in a vibroacoustic solver for analyzing the effects of spacecraft response to the specific Dart field. It can also help in anti-sound analysis and control by allow investigation of potential ANC solutions based on anti-sound speakers. For more information, contact info@interac.fr. Thank you all for your attention.